This is the video lecture of section 8.7 part 1 out of 3 parts of this section 8.7. The first part for math 2520 calculus 2. Okay, so in section 8.5 we learned that we considered Taylor series, not Taylor series, some power series. A power series is a function of x which has this form, kind of infinite degree polynomial. It's not a polynomial, it's non-negative integer power of x, just like polynomial. The thing is that the difference is it can go all the way to infinity. Okay? Well, this is a function of x whose domain is the value of x for which this is convergent series. Okay? So in 8.5 we were introduced to the concept of power series, and then we learned how to get the values of x for which this is convergent, called interval of convergence and radius of convergence. It turns out that your power series has always interval of the set of all numbers of x for which this is convergent is an interval. All right? From around asymmetrically same distance, from a plus r, a minus between them. That r is called radius of convergence. So we learned how to get those radius of convergence and interval of convergence using ratio test. That is a function of x. And then 8.6, we learned for some special type of functions, for a given function of x, we were able to find a power series whose value is same as the given function, so-called power series representation. For not all functions, but some functions, starting with this. This is geometric series. This is true for only this one, so radius convergence 1. Out of this, we can write it this thing as minus x squared to the nth power, right? And then you learn that if you have a power series representation with some radius of convergence, your derivative, in this case, 1 minus, this derivative will be, let's say 1 minus x squared, minus 1 cancel. Its derivative also has a power series representation with the same radius of convergence, in this case 1. And that power series can be obtained by taking term by term differentiation. And also, minus of element of 1 minus 6. Antiderivative will have arbitrary constant, also have as power series representation with the same radius convergence, which can be obtained by taking term by term integration. Okay? So, we were able to get power series representation, a power series whose value is same as the given function. So you're given a function first, and you're looking for power series representation of the given function. But the kind of function we were able to get the power series representation were very limited. Directly, indirectly, it is related to basically 1 over 1 minus x, or some easy manipulated ones from there, or integration or differentiation. Obviously, there are all kinds of functions you cannot use this approach, like sine of x, e to the x, all kinds of functions. Then what are we going to do if you want to get power series representation of general kind of function, when the function is differentiable infinitely many times? By the way, we learned that if a function has a power series representation, then it is differentiable infinitely many times, because the theorem says that its derivative also has a power series representation. Okay? Therefore, we apply that theorem to derivative, then you get another derivative also has a power series representation. You go on forever. So, this section is about how do we get power series representation of general function, not just this kind of function, but any infinitely many differential function. So, we start with this, okay? Suppose that f of x has a power series representation, PSR, power series representation, that is this. Somehow we know that, let's assume, we know that somehow f of x has a power series representation. Then we want to know the coefficient, how this Cn, what kind of form Cn has as a function of n. All right, this is our main question here. How do we get it? Now, if you expand, that would be this. Okay, keep going. So, now if it has a power series representation, then from the main theorem of section 8.6, then, first of all, with some radius of convergence r greater than 0, either some positive real number or infinity. Okay? So then, because it is true for all, that means at least for all x. It could be true even some of the endpoint values, but at least interior points, everything. This is equal. That's what we call having power series representation. So now when x equals a, this was the same. You have both a 0, 0, 0, everything 0 except for c0. Right? So we get this. If you have a power series representation of function f of x, then at least the first coefficient, the constant term, must be f of a. That is what you can derive from that assumption, having power series representation. Now, from the main theorem of section 8.6, if f has a power series representation with radius convergence r, then f prime of x also power series representation with the same radius convergence, right? So, and then that power series representation can be obtained by taking term by term differentiation, right? So if you take a look at this, then C1, 2C2x minus a, and 3C3x minus a squared, 4C4x minus a to the third. If you have another term, 5C a to the fourth. Keep going. Right? Now, this one has also same radius of convergence. This is same, really same, for all x at least interior points. Now, here, in that identity, if you plug in x equals a, what do you get? F prime of a equals x equals a, all 0 except for sigma. So you have, if your f has a power series representation, the coefficient of the x minus a must be f prime of a. Alright? That's what we derive. Now, we apply the same theorem from section 8.6 over here. Then f double prime also, another derivative also has a power series representation with same radius of convergence r. Because of that, if you plug in x equals a, what do you get? If you take the derivative, this means 2c2, 3, 2, c3x minus a, 4, 3, 5, 4. See? X equals a, plugging in x equals a, then f double prime of a equals 2c2. That means c2 equals f double prime of a over 2. So if f has a power series representation, the coefficient of the second power term is f second order derivative at a over 2. Now, we apply the same theorem to this function. That means its own derivative, that will be third order derivative, can be has a power series representation, and that can be obtained by taking term by term differentiation. That would be 3, 2, c3, 4, 3, 2, c4, x minus a, 5, 4, 3, c5, x minus a squared. Because it is true for all x between a minus r to a plus r, by substituting a for x, you get third order derivative at a equals, this is 3 to 1, 3 factorial, c3. So c3 equals third order derivative at a over 3 factorial. Okay, now you see where I'm going. Take another derivative. F fourth order derivative of x also has a power series representation with the same radius of convergence. That would be so that would be 0, 4 factorial c4, right? 5, 4, 2, 3, 2, c5, x minus a, and then higher order terms. So when you have x equals a, fourth order derivative at a equals 4 factorial c4, right? So c4 equals fourth order okay, 4 factorial, 3 factorial, 2 is same as 2 factorial, right? And you can write it C1 also as a first order derivative a over 1 factorial, right? 1 factorial is 1. You can write it C0 as, function, original function. Also, sometimes we use a 0th order derivative, which means function itself. 0 factorial is also defined to be 1. So in the end, you find that an must be nth order derivative at a over n factorial for all n, for all non-negative integer. This is wonderful. That gives you very concise, beautiful formula for an, right? Or Cn. So, if f of x has a power series representation, then that power series must have this formula. That is nth order derivative of f at a over n factorial times x minus a to the nth. So that form of power series is called Taylor series. So Taylor series is just that's theorem 1. if f has a power series representation at A with some positive radius of convergence, then that power series representation must have this form. Your coefficient Cn must have nth order derivative of f at A divided by n factorial. Okay, for all non-negative integer n. And we call it Taylor's series. So, that is if f has a power series representation. Then you have this. That's theorem 1. Okay? Now, so you got this formula. Assuming that f is a power series representation. Now the question is, how do we know a certain function has a power series representation? The question is every function has that property? As long as your function is infinitely differentiable, because if you have a power series representation by the theorem in section 8.6, it must be differentiable infinitely many times. So our question is, if a function is differentiable infinitely many times, does it automatically mean that that function has a power series representation so that we can have this form? We call it convergence series, exactly the same as the given function. That would be a very important question, right? So the answer to that question is, unfortunately, not necessary. There is a function, even though it is differentiable infinitely many times, yet its Taylor series, this formula, is not equal to the given function. Okay? So that means that function cannot have power series representations. Because if we had, then you should have been equal to its power series, all right, representation. The Taylor series formula, the Taylor series must have been equal to f of x. All right? So that's the example I gave you at the bottom of second page. So, this is a little bit advanced, but I want to give you just one example. So if your f of x is 0, if x is greater than or equal to 0, or if x of minus 1 over x squared. If x is going to infinity. No, if x is greater than 0. So, your function f is piecewise function. So, over here your graph is stay at 0. Now, if x is really large, 1 over really large number is almost 0. E to the almost 0 is almost 1. Slightly negative power means slightly less than 1. E to the slightly negative power means slightly less than 1. So, if you draw the graph, so stays at 0 here at 1. As x going to infinity, your graph is almost 1. What happens when x is really small? When x equals 1 e to the negative 1, it's like 0.3 something. Alright, it's going down like this. Then when x is really close to 0, x small number in the denominator, 1 over very small number square will be very large number. E to the negatively very large number, like e to the negative 1000. That would be really small number, right? So as x approaches 0, this one approaches 0 really, really, really fast. Okay? So, This one goes to 0 really fast here. Okay? So that would be the shape. Now, it's beyond this course, but for that one, you can show that f of 0 is defined to be obviously 0. You can actually calculate using derivative definition. You know, f of x minus f of 0 over x minus 0, limit x going to 0. You can show that this is actually 0. And if you take second order derivative, you'll find it is 0. Actually, any nth order derivative at 0 will be all 0 for all n. Actually, this has a very interesting property. At the origin, not only function value is 0, derivative is 0. Yeah, that I can take, right? Tangent, horizontal tangent line there, right before I take off. Not only that, second derivative must be 0, third derivative must be 0, every derivative, every order derivative is 0. So then the Taylor series is the series made of this formula of f is what? Nth order derivative 0 over n factorial x to the n. Everything 0 will be just 0. Alright? For all x around 0. For all x, some positive number. We don't know exactly yet. But, obviously, this is not f of x. Your f of x, yes, it is 0 up to 0, but as soon as x is positive, no matter how small it is, still is positive number. So, this function cannot be equal to this, even a slightest open interval around 0. Because some positive numbers to the right of origin, this is still 0, this is not. So, this is an example that, even though this is differentiable infinite many times, your Taylor series formula, the Taylor series, is not equal to the function. So what does it mean? That means the f cannot have a power series representation to begin with. Because if it had one, then it should have been equal to this Taylor. Because the Taylor series should be the power series representation. So this is very famous counterexample. So a function which has a power series representation with some positive radius of convergence, we call it analytic function. Analytic function at A. Analytic at A. So this function is not analytic at 0. Okay? All right. Now, if A equals 0, your Taylor series, I'm going to write Taylor series over here again. Question mark, the quotation mark, because some functions actually not equal to this. So, nth order derivative of A over n factorial. This is, we call it Taylor series. Taylor. So Maclaurin. Taylor's series of f. Now, if A equals happen to be 0, we give a special name. That is, we call it Maclaurin. Is it MC or MAC? Maclaurin series of f. Okay. Taylor's series or just Taylor series? I think it's just Taylor series. Okay. Again, if we know that this one has a power series representation, then that power series is the power series representation will be just this. Okay? So, example 1, find the Maclaurin series of e to the x. Find the Maclaurin series of e to the x. Okay? Then we know that derivative of e to the x. Any order of derivatives e to the x for all n. Right? And if nth order derivative of 0 is e to the 0, which is 1. So the Maclaurin series for e to the x will be 1 over n factorial x to the n. That's Maclaurin series of e to the x. Now, can we say that they are equal? We don't know yet. Because they are equal only if e to the x has a power series representation, which we don't know yet. Alright? So this is the form of the power series representation using Maclaurin series formula, assuming that e to the x is analytic at 0. So we haven't answered that question yet. Okay? And then we learned that previously this one has a radius of convergence infinity. And I just did it one more time. So using ratio test in the lecture. We have done this one many times. Okay? Now, then how do we know? How do we show that a function like e to the x actually has a power series representation? Okay? Which means that this Maclaurin series actually converges to e to the x. How can we show that? Okay, first of all, what does it mean by that this one converges to e to the x? Now, we define in this infinite power series Tn of x So that means f of a, f prime of a, x minus a, f double prime of a over 2 factorial x minus a squared. Nth order derivative of a over n factorial. In the Taylor series formula, you stop at nth power term. Then it becomes polynomial of n most n degree. It may not be n degree. If this one happens to be 0, then that could be n minus first degree. But it is up to n degree. But even though it may not be degree n, still we call it nth degree. This is the nth degree Taylor polynomial of f and a. Okay? Now, the first remark is that T1 of x is what? This is a linearization of f. Its graph, y equals this, will give you tangent line, right? Slope is f prime of a, slope of tangent line, going through a f of a, right? So it is a tangent line. So this is a linearization. So first degree Taylor polynomial is a linearization, okay? Or linear approximating function of f, okay? As you can see in the lecture notes. So your Taylor series, actually, this one, what is the definition of sum of the infinite limit? That was limit of the partial sum sequence, right? That partial sum sequence is Taylor polynomial, isn't it? Right? So, limit of Taylor series polynomial as n goes to infinity. So that means we keep adding more and more terms, right? The limit of Taylor series nth degree Taylor series polynomial, Taylor polynomial approaches f of x. Is same as Taylor series converges to f of x. So this one converges to f means that f minus Tn of x is getting smaller and smaller, right? If this one close to f, then f minus Tn of x is very close to 0. We call it remaining. Rn of x, f of x minus Tn of x. This is, alright? This is called remainder. Why we call it remainder? Because if f of x indeed same as Taylor series, all right? Let's say your Taylor series, keep going. Keep going. Then this one, oops. Keep going. If Taylor series converges to f, that means same as f of x. The f minus Tn will be this remaining ones, right? If Taylor series converges f, if they are equal, then f minus this thing will be remaining. That's why we call it remainder. It basically is an error from the approximation by the nth degree Taylor polynomial of f. Okay? So f of x is sum, same as this sum. So this Taylor series converges to f of x, means that limit of Tn of x equal to f of x. By definition of sum of infinite series converging to f, right? Sum of this one is f of x. That means the difference between f of x and Tn of x equals 0. That's what it means by Tn approaches f. That means they are differ by a very small number. Differences will be almost getting smaller and smaller to 0. That is precisely remainder. Going to 0. So we want to show that remainder of the Taylor series expansion going to 0. That's what we want to show. Okay? This is remainder of the Taylor series of degree n. Now, let me check the recording. Now, then, so how do we show this one? There's a critical theorem called Taylor's inequality. This is the key for that purpose. Taylor's inequality. This is not too hard to prove, but we decided to skip the proof. Okay? That is, if n plus first order derivative is less than or equal to some constant capital M for all x between R. a minus r to a plus r for all x over here, then this remainder is less than or equal to m over n plus first factorial, and x minus a to the nth power. Again, for all, here, not smart, some positive number d, positive number n, then any x less than or equal to d, x minus a. So that means a plus d, a minus d, everything over here. For all such x values, your Rn of x absolute value is less than or equal to m over n plus first factorial x minus a to the n plus 1. Okay? This is Taylor's inequality. This is the key. Okay? Now, so there's a first remark. This form is quite convenient and is quite has a close relation with Taylor series expansion. Just remark. Suppose that indeed f is analytic. A. That means your f of x indeed same as is Taylor series. So its power series representation can be obtained by Taylor series formula. So f of a nth order derivative of a over n factorial x minus a plus 1 keep going. So then, if this is analytic, so that this is really equal, then f of x minus Tn of x, this is Tn of x, right? So, your Rn is actually absolute value of the remainder. All the remaining terms, all right? But then, if this is the case, now think about the from all the remaining terms, think about the very first term. If you take absolute value of n plus first order over x minus a to the n plus 1. Now, according to this, not just at a, but from a minus d to a plus d for all such x, this is n plus first order derivative is less than or equal to m. This is less than or equal to m. Right? So what? This form, in this theorem, said that the whole remainder, the entire remainder is less than or equal to this expression. But that expression is actually natural upper bound of the n plus first term. The first term neglected in this cut, in this approximation, right? The entire remainder term is actually bounded by the same upper bound for only this n plus first term, right? That's why it is easy to remember. Because from over here, upper bound of this one is capital N over n plus 1 factorial. absolute value of x minus a to the n plus 1. Alright? That's why this looks very natural. Alright? You have seen something similar to this. The size of the entire remainder is less than or equal to size of the first one among them. The very first one discarded in the approximation. That was alternating series estimation theorem, right? If you have an alternating series where absolute value of n is decreasing and converges to 0, then it is convergent. And the remainder out of Sn, if you use Sn as an approximation, true value S minus Sn, called also remainder at the time, the absolute value remainder is always less than or equal to n plus 1 absolute value. The first term discarded, less than or equal to. Remainder will be the everything together. Yet in size of the whole remaining terms will be smaller, less than or equal to the very first term discarded. It's quite similar, right? Alright. So we got this one. Now let's prove at least e to the x is really convergent. It's analytic. Okay? There's the last example. Example 2. Let's see. Let's show that e to the x is analytic at 0. That means e to the x is equal to its own Taylor series. The sum of Maclaurin series or Taylor series. Taylor series at A. Okay, general case at A. For all A. So again, if this is e to the x, then nth order derivative of x also e to the x. Alright? So let that d be any positive real number. Then, so what does it mean by this? X minus the absolute value is less than or equal to d means, right? X minus between plus minus d. So that means a minus d, a plus d. Okay? For those ones, f of n plus 1, I want to find capital N, corresponding capital. That is just e to the x. Always e to the x. This is increasing function. This, for all such x, is less than or equal to e to the a plus d. For all such x. Alright? Alright, so this is our capital M, right? For all x between a minus d to a plus d, n plus first order derivative of this function e to the x is always less than or equal to this number, e to the a plus d. Alright? So, therefore, according to Taylor's inequality, the size of the remainder, nth remainder, is less than or equal to m, e to the a plus d, over n plus 1 factorial, x minus a to the n plus 1. Alright? For all such x. Well, this x minus a to n plus 1 is less than or equal to d, right? The largest possible case when it is exactly d. So this is e to the a plus d, d to the n plus 1 over. So, what do you see? As n goes to infinity, what happens? D is fixed number, a, d, these are all fixed number, n, only n grows. Something to be d, n plus 1, exponential function versus factorial function. Obviously this one trumps everything. This one goes to 0 as n goes to infinity, right? No matter how large D is, no matter how large or small A is. For all A and D, right? So, this one converges, right? So limit of Rn is 0 for all x in this, for all x in here. Your Rn of x goes to 0. But you can choose D as large as you want. Still it is same argument, right? Maybe it takes larger n, more terms to converge, but still goes to 0. So that means this one converges to e to the x. Okay? Your Taylor series converges to e to the x. For all real number. Okay? Radius of convergence is infinite. So we just proved that e to the x is analytic at 0 or any point A. Alright? Using Taylor's inequality. Alright, that's the end of first part out of 3 parts. First part of section 8.7. Alright? And then there will be 2 more sections, 2 more parts of section 8.7. Alright. So, I'll see you later.